Hello and welcome to non-IITian. This is going to be the third lecture in the series on group theory, and pardon me because there might be some background noise of some because there is some bridal ceremony going on beside my house. Nevertheless, let us just continue our discussion. So in the last lecture we were discussing about cyclic groups, and the first thing which I want to discuss today is the following. That is a very brief introduction to group of units. The first thing which I want to discuss is group of units. Okay, so what do I mean by an unit? So this will be more clear once you are familiar with ring theory, but nevertheless we can give a formal description of group of units in groups as well. So consider Zn. So we know that Zn consider elements 0 1 till n minus 1 under addition modulo n, right? Now what I want to do is that now we want to construct a multiplicative group out of the elements in Zn, and that group is what we call the group of units. Okay, so basically an element, if it has a multiplicative inverse, okay, so it's an additive group, right? So an element here, if has a multiplicative inverse, because obviously there is a natural multiplication which we can apply to these elements, that is multiplication modulo n. So if it has a multiplicative inverse, that is, I have some element, for an element a I have some element b, so it should be congruent to 1 modulo n. In that case we call that element to be a unit. Okay, so this is in some sense should be the collection of all units, okay. And obviously if we form a collection of all units, then that will abide by every property of a group under multiplication, right? Because 1 is obviously a unit, because 1 times 1 is congruent to 1 modulo n, and by definition itself, since we are talking about units, so every element will have a multiplicative inverse. Multiplication is associative by its nature, and it will obviously be closed, because if I have suppose if I have AB is congruent to 1 modulo n, and suppose I have CD, this is congruent to 1 modulo n, so what can I say about A and C? So what I can do is that I can first take D, so by associativity CD will be congruent to 1 mod n, then I can take B, so this will be congruent to 1 modulo n. So it's obviously closed, right? Product of two units will still be a unit. So in some sense what we can also see is that AC inverse will be nothing but C inverse A inverse, which is the typical property of inverse elements, right? So it's a typical property of inverse elements. These are pretty elementary properties of inverses, because you can see that AB inverse is nothing but B inverse A inverse, quite easily observable. Okay, fine. Now, so UN is the basic notation of the elements of the unit elements of Zn. So what should be typically the elements here? So the first thing, observe that if for example, suppose say A is an element in Zn, and let us just avoid 0 because it's the element 0 is of no use, obviously. Now so if A is a non-zero element from Zn, suppose let's say the GCD of A and N is D. Okay, yeah. So now, okay, so I want a specific condition for A to be a unit. Are you getting my point? Now observe that if the GCD of A and N is 1, What does that mean? So that means that there exists x and y in Z such that a times x plus b times y, b times n is equal to, plus y times n is equal to 1, but that is exactly congruent to ax, or rather, which implies that ax is congruent to 1 modulo n. I'm just putting x bar here because so x bar is x mod n, and that should be an element of Zn, right? For example, suppose we take Z4 and I choose the element 3, right? Then we know that 3 and 4 have GCD 1, and 3 times 3 minus, let's say plus or minus 2 times 4 is equal to 1. So from here we can conclude that 3 inverse is just 3. I hope it's clear now. Okay, fine. Now, so what we can conclude is that so this implies that if the GCD of A and N is 1, then that implies that A is a unit. But what about suppose A is a unit? Suppose A is a unit. What does this imply? So this implies that there exists some B in Zn such that AB is congruent to 1 modulo n. But that means that there exists some R in Z such that AB minus R times n is equal to 1. But what does that imply? That implies that the GCD of A and N must necessarily be 1, right? Because the GCD will divide the left hand side, because the GCD of A and N, if it's D, so it will divide A, so it divides AB. It divides N, so it divides Rn. So in particular, it divides AB minus Rn, so it also divides 1, and hence it is exactly equal to 1. And so hence we conclude, so therefore A in Zn is a unit if and only if the GCD of A and N is 1. Therefore, what can we say about Zn cross, or by our notation Un? So this is exactly the collection of all those elements in Zn such that the GCD of A and N is 1. Okay? And so therefore, what should be the cardinality of U of n? So it should be exactly phi of n, which is the Euler-Toshen function, which counts the number of elements co-prime to n less than n, right? Right. Okay. So now a very important question is that suppose we know that Zn is cyclic. So natural question would be, is Un cyclic? Is Un cyclic? Now Un is not always cyclic, so it is not true in general. So for example, let us choose, so let me just take a good color. Yeah. So let us choose Z8. So what should be the elements in U of it? So these should be all the elements which are co-prime to 8. So it should be necessarily 1. Okay, wait a second. Right. So it should be 1. Yeah. Sorry. So 1, 2 won't be it. 3, 4, no, 5 and 7. Right? And it can be easily observed that phi of 8 is 4. So yeah, so it is good, right? Now is it cyclic? So observe that for it to be, what is the necessary condition for it to be cyclic? For it to be cyclic, I must have an element whose order is exactly equal to the order of the group. But as we see that 3 squared is 9, which is congruent to 1 modulo 8. So therefore the order of 3 is 2. 5 squared is equal to 25, which is also congruent to 1 modulo 8. So therefore the order of 5 is also 2. And 7 squared is 49, which is again congruent to 1 modulo 8. And hence the order of 7 is also 2. So none of the elements have order 4. So will it be cyclic? It won't be cyclic, right? So there are only 2 groups up to isomorphism, in of order 4. So there are only two groups of distinct algebraic properties, and all other possible groups of order 4 will be one of these groups. So groups of order 4 are either cyclic or of the form 1a, b and ab, such that a squared equals to b squared equal to ab squared is equal to 1. That is all the non-trivial elements, non-identity elements of order 2, and this is called the V4 group, or often called the K4 group. It's called the Klein 4 group. So what we have typically seen that U8 is basically a Klein 4 group, and it's not cyclic group. So there's a very fine condition, probably it was introduced by Gauss. It says that UN is cyclic if n is one of these numbers. So it's 1, 2, 4, p to the power k, and 2 times p to the power k for odd prime p. For odd prime p, and k is greater than or equal to 1. So these are the only cases when UN is cyclic. So for example, suppose I ask that is U5 isomorphic to U8? Is it so? So observe that 5 is of the form 5 to the power 1. So it's of this form. Hence this group is cyclic. While we just proved that this isn't cyclic. In fact, it also is clear from the possibilities of this particular thing that it shouldn't be cyclic. So it isn't cyclic. So there cannot be isomorphisms. They cannot be isomorphic, because we discussed on the surface level in the previous lecture that isomorphism means that they are algebraically the same, structurally they are same. So if one of them is cyclic, the other also has to be cyclic. If one of them is abelian, the other also has to be abelian, so on and so forth. Every algebraic property of one of the group must be mimicked by the other group under isomorphism, right? So it's not true. Okay, so I hope this particular discussion is clear. So that was a quick discussion of group of units. I did not want to waste a lot of time. Not waste, I wouldn't use the term waste, but to involve much more time to discuss group of units. Nevertheless, let us start with the thing which I wanted to discuss today, which is the first thing would be Lagrange's theorem. And to construct Lagrange's theorem, we will undergo a very, very sophisticated construction of what we call quotient groups, or at least cosets. Okay. So let us observe very carefully. Suppose G is a group and H is a subgroup of G. Okay. What we do is that we define an equivalence relation. We define an equivalence relation on G. Okay, I forgot to mention something in the previous lecture. I should have mentioned it. I will mention this because I require Lagrange's theorem to mention that. So we define an equivalence relation on G as follows. So what we do is that we say that two elements are equivalent if and only if so y inverse x, this is in H. Okay. This is the way we define an equivalence relation on G. Now it's a very, very easy to check that this is in fact an equivalence relation, because every element will be related to itself, because one is in H. Since H is a subgroup, you can take the inverse of this to, or rather you can just this is a very trivial exercise to show. So show that. Now I'm actively giving out exercises because that's the best way to learn things. So show that this is an equivalence relation. This is an equivalence relation. Okay. So what should be the equivalence class of an element X? So it should be the collection of all those elements Y in G such that y is related to x. In other words, this is the collection of all those elements y in G such that x inverse y is in H. So this is the collection of all those elements y in G such that y is of the form xh, where h is in H. So in other words, this is the collection of elements of the form x times h such that h is in capital H, and this is what we define to be this particular set. And these sets are called the left cosets, or rather a left coset in this context, of H in G. And on a similar note, if I can try and just revert out this definition to get hold of what we call the right cosets, that is also something you can do. So I'm just giving another exercise to show a similar construction to form sets of the form hx. So that should also be the same definition. So hx would be elements of the form h times x. Okay, is it clear? And we define G by H as the collection of all left cosets. So I'll just misinterpret this particular notation, because if you have read an abstract algebra book, then you'll see that this particular notation is what we use for quotient groups, and that is the reason why I just use the subscript L to define this to be nothing but the collection of all left cosets, and I'm not endowing it with any structure at all. It's just a collection of sets. So as X traverses over all the elements in G. So this is the collection of all left cosets of H in G. Now we know that there's a very interesting property of equivalent classes, that is they partition the set, right? So therefore I can write G as disjoint union of these left cosets as X traverses over all G's. Now if G is finite, then what can we do? Then the cardinality of G should just be the sum of the cardinalities of these left cosets as X traverses over G, right? Is it clear? Okay, fine. Now what we do is that we do a very interesting thing. Now consider a function phi from, let's say, h to xh. So what we do is that we choose an element h and we map it to x times h. So it's a very natural construction. Now is this set well defined? So it's well defined by very definition itself. So it's well defined. Now is it injective? Now observe that if phi of h1 is equal to phi of h2, that would imply x times h1 is equal to x times h2, but by cancellation h1 is equal to h2, because you can cancel out elements, right, by multiplying with inverses. So let me use another color here. So if I have a times b is equal to a times c, so that would imply a inverse times ab is equal to a inverse times ac, but then by associativity I have a inverse times ab is equal to a inverse times ac, which would imply b is equal to c, right? Okay, that's called the cancellation. In fact, if you study very good books on abstract algebra, you will see that cancellation law holding, if you have a structure, if you have a monoid, for example, and the cancellation laws hold actively, then it automatically forms a group. You need not mention that inverses exist. Okay, that's a very that's sort of a weaker axiom, but it's as strong as required. Nevertheless, we have this. Now so it's injective, right? So therefore it's injective. Now also observe that, so this is from definition itself. Now if I choose an element, so by definition itself it's surjective, right? because any element in the codomain will be of the form x times h, and it will just be the image of the set, image of the element h. So by definition it's surjective, so therefore it's a bijection. So it's a bijection, and h and xh both should be obviously finite sets. So what does that mean? That means the cardinality of h must exactly be equal to the cardinality of x of h, and hence we have the following. So therefore the cardinality of G, which was the collection of all xh, now I slightly modify the sum, because summing over all all x traversing over G is same as summing over all distinct left cosets, because obviously two left cosets might coincide at some point, right? So what should this imply? So this should imply, or rather this should be equal to the cardinality of H, because we just proved this, over all distinct left cosets of H in G. So this should be equal to the cardinality of all the left cosets, collection of all the left cosets, times H, and this is what we define in this form, G colon H, and this is called the index of H in G, the number of distinct left cosets of H in G. But what does this essentially prove? So this immediately proves, this implies that the cardinality of H divides the cardinality of G, and this is what we call the Lagrange's theorem. Is it clear? So now you can phrase out the theorem in your own words, but nevertheless this is exactly what Lagrange's theorem is. And there's a very important corollary of the Lagrange's theorem. Every group of prime order is cyclic. Okay, every group of prime order is cyclic. Let us prove this. Proof. So let G be a group, and let the cardinality of G be P, where P is a prime. Okay, so I need to show that it's cyclic. So let A be a non-identity element from G, and let H be the cyclic subgroup of G generated by A. Okay, now by Lagrange's theorem, the cardinality of H, which is exactly equal to the order of A, this should divide the order of G, which is a prime P, and we know the only factors of P are 1 or the prime P itself. So this implies that the order of A is either 1 or P, but order of A equals to 1 would imply A is equal to 1, which is not the case. This is not possible, which implies that order of A must be equal to P, but that implies order of H must be equal to P, which is exactly equal to the order of G, which would imply H is exactly equal to G, and which would imply that G is nothing but the cyclic group generated by A, and therefore every group of prime order are cyclic, and hence obviously ZP is a cyclic group, or any group of prime order will be cyclic. Is it clear? Okay, fine. Okay, so that's about the Lagrange's theorem, and there are many consequences of Lagrange's theorem. One of the consequences is another corollary, you would say, is that for all A in Z, I can talk about positive integers. There's no issue, and n is a natural number. A n is equal to 1, that is the GCD of A and n is 1, then A to the power phi of n is congruent to 1 modulo n, and this is called the Euler's theorem. So it's the generalization of the Fermat's little theorem. Okay, and how do we prove this? So proof. So consider the group U of n, right? Then the cardinality of U of n is phi of n, and by definition of U of n, and if A is in Un, or rather I can say it in this way then, and if A is in Z plus, such that GCD of A and n is 1, then obviously the residue class of A, so this is A mod n, is inside Un. Okay, are you getting my point? So it's inside Un, but then by Lagrange's theorem, the order of A bar must divide phi of n, and we know that by this property A bar to the power phi of n must be congruent to 1 modulo n, but that should imply that A to the power phi of n must also be congruent to 1 modulo n, because A bar is nothing but A mod n. Okay, is it clear? Are you getting my point? Fine. So that's the proof. Okay, and there are many typical consequences of subgroups. So we will be coming up with problem sessions, then we will be discussing more such properties as we'll encounter them. But nevertheless, for more involved study, if you have interest in doing so, you can consult books like I had mentioned one book in the previous lectures. You can just consult Gallian Abstract Algebra book. Yeah. So I'm starting with group homomorphisms now on a more formal note. Let's see how much we can do. I'm just intended to give the definition in this particular lecture. Okay, let me not get involved into group homomorphism. We will be strictly doing that in the next lecture. For now, let me introduce the notion of normal subgroups. Okay, normal subgroups. So what is a normal subgroup? So definition. So let G be a group, and let H be a subgroup of G. We say that H is a normal subgroup of G if and only if the left cosets are also right cosets for every element G in G. That is, G inverse is equal to H for every G in G. Okay, which is equivalently saying that G inverse is contained in H for every G in G, because the other inclusion is trivial. H will obviously be contained within G inverse for G is equal to identity. Right? So in this case, we say it to be a normal subgroup. And why is it important? So definition. This is the reason why normal subgroups are important, is that let G be a group and H be a normal subgroup of G. So this is the way we denote normal subgroups. Then G mod n, which is exactly, okay, so G mod H, which is exactly the collection of all left cosets of H as X traverses over G. But by the definition of normal subgroups, we know that this is also exactly the collection of all right cosets of H in G, forms a group with respect to the operation. So what should be the most obvious operation you would go for? The operation which abides by the usual operation on G. So if I have two elements XH times YH, I should be getting XY times H. Okay. Now, the way the reason why normal subgroups have actually come up into existence, there are two basic motivations behind that. First thing is, we have seen, or we will be eventually seeing, but I have already introduced normal subgroups, so it won't make such a sense in the next lecture, but we'll see later. The kernel of a homomorphism is normal in G. So this was a property which was first observed in kernels of homomorphisms. And secondly, so we intended to make G mod H L. So H was a random subgroup of G, a group. But this operation wasn't well defined, except when we allowed xh to be equal to hx for every x in G. Okay, so this is the second way we sort of thought about such subgroups, and in fact we found out that such subgroups are of extreme importance in some sense. Okay. A very important property of normal subgroups is the following lemma. That is, if G is a group and H is a subgroup of G such that the index of H in G is 2, then H has to be normal in G. And the proof is quite easy. Proof, since the index of H in G is 2, what does that imply? That implies that G mod H, you can take the left coset, so this should be only H and GH for some G in G. Okay, and also G mod H R should also be H and some H X, let's say. And we know that each of these are equivalence classes, so also G is the disjoint union of each of these elements. So H of X, right? Is it clear? But here's a good catch. Observe that we are explicitly writing this out since G is not in H, because if G was in H, then GH would necessarily be H, right? By the closure property of H. So G is not in H, and this also is possible because X is not in H. So what does that mean? So there are only two possible equivalence classes. G is not in this equivalence class, so G is not in this equivalence class. X is also not in this equivalence class, but there is only one more equivalence class possible. So that means G and X are both in this equivalence class, or in this equivalence class, whatever you say. In other words, G and X are equivalent. So that means G of H, or rather H of X, is same as H of G, H times G. Are you getting my point? So this is same as H disjoint union HG. But what does that imply? That implies that G minus H is equal to G of H and is also equal to H of G. So this implies G of H is equal to H of G for every G in G. Because if G is in H, then it's trivially same. If G is not in H, then it holds by the way we proved it. So this implies that H is normal in G. Proof. A very important property of normal subgroups is the following. We're not going to prove it, but we're just going to state it. So theorem, if G is a P group, so we will be getting involved into what P groups are later. That is, the order of G is some P to the power N for P prime and N some natural number. Then G has subgroups of order 1, P squared, all the way up to P to the power N. So it has subgroups of all possible divisors of the order of G, each of them being normal as well. Each of them being normal. So this year CSIR NET December 2025 asked a very beautiful question, that is, there for every n in natural numbers there exists a group G such that G has exactly n subgroups. And what you can observe is that it's true, as if order of G is p to the power n minus 1, it works. Because after all, these are the only possible orders, right, by the Lagrange's theorem. And we are getting all these subgroups. So these are the only possible subgroups, right, of these particular orders. So if I take the order of G to be p to the power n minus 1, we'll get exactly n subgroups. So it's true, right? Okay. Should I talk about some more things at this point? Some examples, I would say examples. So observe that if G is an abelian group, then every subgroup is automatically normal, right? Every subgroup is normal. Okay. Now, in the next lecture, when we will be not the next lecture, probably next to next lecture, when we will be introducing symmetric groups and dihedral groups, we'll see more examples of normal subgroups. But let me just introduce very briefly the notion of dihedral group by an example. Suppose I choose a triangle, or let me just choose a square. Oh, this is just a planar square. And suppose we name its vertices as 1, 2, 3, and 4. And what we do is that we apply some operations on it. And what are the operations? So there are two fundamental operations. One is R, which is rotation by 90 degrees anti-clockwise. Okay, so what we do is that applying R once to this square would send 1 to 2, 2 to 3, 3 to 4, and 4 to 1. Applying it twice would send 1 to 3, 2 to 4, and applying it thrice would send 1 to 4. Then it would send 2 to, so it will send 1 to 4, it will send 2 to 1, it will send 3 to 2, and it will send 4 to 3, right? And finally, if you apply it 4 times, it will be 1. So the order of R will be 4. And what we do is that another operation is a reflection. So I choose a random axis like this, and I take reflection. So S is reflection about the axis. Okay. And then I consider the following set. So I consider 1, R, R squared, R cubed, the possible rotations. I take S to be the reflection. Now it is clear that the reflection is of order 2, because if you reflect twice about a fixed line, so you will get back the same image back. So it's of order 2. And now what we can do is that we can compose out these two elements. So I have SR, SR squared, and SR cubed. Okay. And there's a very important property which you can see here, is that SR is same as RS inverse. RS equal to SR inverse. And it holds for every element. Okay. It holds for every element. That is, you'll see that you have R, so R inverse will be basically R cubed. Then you will see that R cubed S would be equal to SR. You'll see that R squared is equal to SR squared, because R squared has inverse R squared itself. So this is called the dihedral group D4, and it preserves the symmetries of a regular square. Okay. And from here, what we can find, that this particular group 1R, R squared, R cubed, so which is nothing but the cyclic group generated by R. So this is the group, or rather the subgroup of rotations. Observe that the index of the cyclic group generated by R is 2. So which implies that this is in fact a normal subgroup of D4. And this is true for every dihedral group. Okay, so we can define dihedral groups in general by mimicking the same exactly same thing as we did. Okay. Yeah. So yeah. Do I need to discuss something more about examples at this point? I don't think so. At this point, I don't think there are more things I necessarily need to discuss. Nevertheless, I'm giving a very brief exercise. Question: prove that all groups of order 1, 2, 3, 4 and 5 are abelian. All groups up to order 5 are abelian, and this should be quite easy to prove by whatever we have done up till now. Okay. Is there some more exercise I would like to give? Let me just think once. Okay, a very brief exercise again. So let G be a group. Let ZG be defined as the collection of all those elements A in G such that A commutes with every element for all x in G. So A commutes with every element in G. So clearly if G is abelian, then ZG is exactly equal to G. So it's called the center of G. It's called the center of G. Next, consider this particular CG of A, which is the collection of all those elements G in G such that G commutes with A. So this is called the centralizer. So this is called the centralizer of A in G. And finally, consider this set NG applied to a subset A. So it's a subset. So A is a subset of G. So it's the collection of all those elements G in G such that G commutes with A as cosets. Okay, and it's called the normalizer of G in a normalizer of A in G. And observe that if A is a singleton set, then normalizer is exactly the centralizer. The question is, verify which are contained in which are contained in which, and which of the provided sets are normal in G. Okay, so that should be a clean enough exercise. Should I give one more exercise? I'm just framing up a question. Okay, one more exercise, last exercise. Okay, if prove that if G mod its center is cyclic, then G is abelian. Okay, so that's all for this lecture. So I'm given three exercise. Please try and do this on a serious note, because all of these are actually important properties, but framing these as questions will actually help you enhance the subject more. Okay, fine. So meet you guys in the next lecture. In the next lecture, we will be talking about homomorphisms and isomorphisms.